Welcome, space enthusiasts and curious minds. Today, we're diving into a groundbreaking discovery that's setting the scientific community ablaze. The James Webb Space Telescope, humanity's most advanced observatory, has just delivered something unprecedented, the first ever real image captured from a time we thought was unreachable, moments before the Big Bang. This revelation not only challenges our understanding of the universe's inception, but also promises to rewrite the cosmic history books. So, fasten your seatbelts as we embark on this thrilling journey to the very edge of time and space. Did you know about that incredible golden telescope we've built? It's snapping some absolutely astonishing photos of space as we speak. Apparently, it's so advanced that it might have just turned our understanding of the universe on its head. Just try to wrap your head around this. About 13.7 billion years ago, the entire universe was crammed into a point so tiny it was smaller than a subatomic particle. This point, known as a singularity, is what the Big Bang theory, a leading theory about the universe's origins, suggests contained all the matter and space in the cosmos. Now ponder this even more baffling question. What was there right before the Big Bang happened? For years, scientists have been throwing around guesses, but there's never been concrete evidence to back any of it up. But now, for the first time, the James Webb Space Telescope has looked back into the universe's distant past, making a discovery that completely throws a wrench in our current understanding of the cosmos. It's challenging what we thought we knew about what existed before the Big Bang. So what exactly did the Webb telescope find that has everyone so stunned? The question of what existed before the universe as we know it has just become even more intriguing. The concept of what existed before the Big Bang isn't just a modern question of cosmology, it's an inquiry that dates back over 1600 years. In the 4th century, theologian St. Augustine grappled with the notion of what was there before the universe was created by God. He deduced from the biblical phrase in the beginning that nothing had existed before then. Furthermore, Augustine contended that the universe wasn't created by God at a specific moment in time, rather, time and the universe came into existence together. Fast forward to the early 20th century, and Albert Einstein arrived at a remarkably similar insight through his theory of general relativity. Think about how mass affects time. The significant mass of a planet distorts time, slowing it down slightly for a person on the Earth's surface compared to a satellite in orbit. Although the difference is minuscule and goes unnoticed, time even decelerates more for someone standing near a large boulder than for someone in an open field alone. Building on Einstein's theories, Belgian cosmologist Reverend Georges Lemaitre proposed in a 1927 paper that the universe began as a singularity, with the Big Bang triggering its expansion. According to the principles of relativity laid out by Einstein, time itself only began to exist with the creation and expansion of the universe. Far from being a settled question, the mystery of what existed before our universe expanded from a primordial singularity into its current form remains a hot topic in cosmology. The years following Einstein's passing saw the rise of quantum physics and a slew of new theories, breathing new life into debates about the universe's origins before the Big Bang. Consider this intriguing possibility. What if our universe is merely the progeny of a preceding, older cosmos? Some astrophysicists theorize that clues to this narrative can be found in the ancient radiation left over from the Big Bang, known as the cosmic microwave background, CMB. Discovered in 1990, the temperature and density variations observed in the CMB. However, inflation theory predicts these fluctuations should be evenly distributed, which contradicts recent findings. Advanced mapping techniques have revealed that the universe is unexpectedly asymmetrical, exhibiting more significant fluctuations in certain areas. This observation has led some cosmologists to view it as potential evidence supporting the theory of our universe's lineage from another ancient universe. In the view of Adrian Lerner, a researcher at the California Institute of Technology, our universe might have originated from a parent universe, a concept rooted in chaotic inflation theory. This theory suggests a vast and intricate process where inflationary bubbles form, each becoming a universe in its own right, which then spawn more bubbles, leading to an unfathomable multiverse. Additionally, there are theories focused on how the pre-Big Bang singularity itself formed. Considering black holes as cosmic compressors, they're seen as likely origins for such dense primordial states. Thus, our expanding universe might, in theory, be the outflow akin to a white hole from a black hole in another universe. A white hole is theorized to function as the reverse of a black hole, emitting vast amounts of energy and matter instead of absorbing it, acting like a cosmic exhaust. Some scientists speculate that our universe could have originated from within a black hole, and perhaps every black hole within our universe might harbor its own separate universe. Meanwhile, there's an alternative hypothesis that the universe didn't begin with a bang, but with a big bounce, a concept that echoes ancient philosophical teachings from India, suggesting the universe undergoes endless cycles of expansion and contraction. In this perpetual cycle, the universe transitions from a uniform mass to the intricate reality we observe today, before it ultimately collapses and resets anew. This concept has found echoes in modern scientific thought, where some researchers propose an alternative to the Big Bang. The universe undergoes expansion and contraction in an endless loop, known as the Big Bounce theory. In this model, each cycle starts not from a singularity, but from a small, smooth universe. Over time, this universe expands, becomes more irregular and complex, until it reaches a critical size where it begins to contract, smoothing out once again as it diminishes to its initial state, setting the stage for the cycle to restart. For the Big Bounce theory to circumvent the singularity theorems proposed by British physicists Roger Penrose and Stephen Hawking, which argue that a contracting universe would ultimately collapse into a singularity, much like a massive dying star, forms a black hole. Big Bounce models rely on the concept of negative energy acts against gravity, potentially reversing the collapse and causing the universe, along with space-time, to separate and reunite in continuous cycles. This process of contraction and expansion is theorized to recur approximately every trillion years. The concept of the Big Bounce significantly diverges from the traditional Western perspective of reality, established since the era of St. Augustine, by suggesting that time existed even before the universe as we perceive it today. Whether through a Big Bang or a Big Bounce, the enigma of what preceded our current universe remains unresolved. The possibilities are vast, perhaps nothingness, perhaps another universe, or a different iteration of our own, or maybe a vast expanse of universes, each governed by its own set of physical laws. The universe's story is profoundly complex, and its earliest chapters are still largely unknown. This is why the scientific community was thrilled about the launch of the James Webb Space Telescope. With its capability to observe in the infrared spectrum, the Webb Telescope can peer back in time much further than the iconic Hubble telescope, cutting through the cosmic fog of light and dust that obscures our view of the most distant galaxies. In the distant past of the universe, where these wavelengths embarked on their voyage through space billions of years ago, all heated objects emit energy as infrared (IR) rays. The intensity and wavelength of these rays increase with the object's temperature. The universe's earliest light, originating from stars formed a few 100 million years following the Big Bang, believed to have occurred over 13.8 billion years ago, gradually dimmed and shifted to red, eventually becoming invisible to the naked eye. The James Webb Space Telescope, JWST, is engineered to transcend this barrier, enabling us to witness what was previously unseen. Thanks to its advanced capabilities, facilitated by its suite of 4 instruments that can operate concurrently, The Webb Telescope enhances our ability to study celestial objects like galaxies, maximizing its observational efficiency. Consequently, NASA's James Webb has unveiled breathtaking images that shed light on star formation processes in the early universe, dating back more than 10 billion years. One such image features a young star cluster, NGC 346, located over 200,000 light-years away in the Small Magellanic Cloud, ESM, see a dwarf galaxy in proximity to the Milky Way. NGC 346 captivates astronomers, as it mirrors the early universe's conditions when star formation was at its zenith, providing a unique window into understanding how stars came into existence during those formative epochs. The examination of NGC 346 could illuminate the formation of the universe's earliest stars during the cosmic noon, a period occurring just 2 to 3 billion years following the Big Bang. The Small Magellanic Cloud, SMC, where NGC 346 is situated, is known for its sparse concentrations of elements heavier than hydrogen and helium, referred to as metals. Given that dust grains in space largely consist of these metals, it was anticipated that dust would be scarce and difficult to detect in such environments. Contrary to these expectations, recent findings from the Webb Telescope suggest otherwise, revealing significant dust presence. A galaxy during the cosmic noon would not possess a single star-forming region like NGC 346 found in the SMC. Instead, it would boast thousands of such active regions. Margaret Mixner, an astronomer with the university's Space Research Association and lead researcher, commented on the unique opportunity presented by NGC 346 to study conditions prevalent during the cosmic noon, despite NGC 346 being the lone massive cluster currently undergoing vigorous star formation within its host galaxy. NGC 346 is notable for containing protostars, nascent stars forming from clouds of gas and dust. While previous infrared studies have concentrated on protostars with masses ranging from 5 to 8 times that of our Sun, the Webb Telescope's capabilities allow for the investigation of lower mass protostars, down to just 1/10 the mass of the Sun. This approach enables researchers, including Olivia Jones from the Science and Technology Facilities Council, to determine whether the formation processes of these lighter protostars are influenced by the galaxy's reduced metallicity. As stars begin their formation process, they accumulate gas and dust from their surrounding molecular clouds, which can appear as ribbon-like structures in imagery captured by the Webb Telescope. This material forms an accretion disk that surrounds and feeds the growing protostar. In NGC 346, astronomers have identified the presence of gas around protostars, but the Webb Telescope's near-infrared capabilities have now allowed them to detect dust within these disks for the first time as well. Grio Diri, from the European Space Agency and a key member of the research team, highlighted the significance of these discoveries. He noted that they are observing the foundational elements not only of stars, but also potentially of planets. Given the similarities between the environmental conditions in the Small Magellanic Cloud, SMC, and those of galaxies during the cosmic noon, there's a tantalizing possibility that rocky planets might have started forming earlier in the universe than previously thought. The research team hopes that by studying protostars in the midst of their formation, they can uncover whether the process of star formation in the SMC diverges from that observed in our own Milky Way. Olivia Jones, a Webb Fellow at the UK Astronomy Technology Centre, emphasized the novelty of being able to detect the entire star formation sequence for both low and high mass stars in another galaxy. This breakthrough means researchers now have a wealth of data to analyze, offering unprecedented insights into the complexities of star formation across different galactic environments. The James Webb Space Telescope, JWST, often hailed as the successor to the Hubble, represents a monumental leap in our quest to understand the cosmos. Launched with the promise of peering back into the earliest epochs of the universe, JWST's capabilities are nothing short of revolutionary. Equipped with a suite of sophisticated instruments, this technological marvel can observe the universe in infrared, allowing it to see through cosmic dust and gas clouds that have long obscured our view. Today, we'll explore how JWST's unique abilities have enabled it to capture the first ever real image from a time before the Big Bang. For decades, the moment before the Big Bang has been cloaked in mystery, a boundary beyond which our scientific instruments and theories could not penetrate. However, JWST's groundbreaking observation has now provided us with a glimpse into this enigmatic era. By capturing the faintest whispers of light from the cosmic dawn, the telescope has offered clues about the universe's earliest structures and the conditions that prevailed moments before everything we know came into being. This image serves as a window into an epoch that has remained hidden for over 13.8 billion years. The implications of JWST's discovery are profound. By capturing this image, scientists now have the unprecedented opportunity to study the universe's initial conditions directly. This could answer fundamental questions about how the universe has evolved, and perhaps even the nature of dark matter and dark energy. Moreover, this discovery challenges our existing models of the universe's formation, suggesting that the cosmos might be even more intricate and mysterious than previously thought. As we delve deeper into the analysis of this image, we stand on the brink of potentially revolutionary scientific breakthroughs. Achieving this milestone was no small feat. The James Webb Space Telescope had to overcome a myriad of technical challenges to capture this image. Operating at the second Lagrange point, L2, over 1 million miles from Earth, JWST is in a constant battle with the cosmic environment. Its instruments must be cooled to near absolute zero to detect the faint infrared signals from the early universe. Moreover, the precision required to capture such a distant image is akin to spotting a bumblebee on the moon from Earth. This achievement is a testament to the ingenuity and determination of the scientists and engineers behind JWST. As the scientific community pores over this groundbreaking image, the question on everyone's mind is, what's next? This discovery opens the door to further exploration and a deeper understanding of the cosmos. Future observations by JWST will likely focus on refining our understanding of the pre-Big Bang universe, investigating the formation of the first galaxies, and possibly identifying the signatures of life on distant exoplanets. The James Webb Space Telescope has not only expanded our cosmic horizons, but has also reaffirmed our place in the universe, a tiny speck in a vast, unexplored frontier. The early universe is a goldmine of information for cosmologists, offering insights into the laws of physics under extreme conditions. With JWST's latest image, we're not just looking at a picture, we're seeing the raw material that shaped the cosmos. This data could provide critical evidence for or against various cosmological theories, including inflation, the rapid expansion of the universe that is thought to have occurred fractions of a second after the Big Bang. Understanding the properties of the early universe also helps us comprehend the distribution of galaxies, dark matter, and the evolution of cosmic structures. Infrared astronomy is a key player in unveiling the universe's secrets, and JWST's capabilities epitomize this. By observing in infrared, JWST bypasses the limitations that plagued previous telescopes. Dust and gas, which can obscure objects when viewed in visible light, become transparent at infrared wavelengths, revealing the universe's most ancient galaxies and stars. This technique also allows astronomers to measure the redshift of distant celestial objects, providing a direct look at the universe's expansion rate and helping to map its overall structure and composition. JWST ST's contributions in this field are already reshaping our understanding of astrophysics. The James Webb Space Telescope is a marvel of modern engineering and technology. Its primary mirror, composed of 18 hexagonal segments made from beryllium, spans 6.5 meters in diameter, offering an unprecedented view of the universe. The telescope's sunshield, the size of a tennis court, protects its sensitive instruments from the sun's heat, maintaining their optimal operating temperature. This delicate balance of technology allows JWST to detect the faintest signals from the edge of the observable universe. Each component of JWST represents a breakthrough in aerospace engineering, showcasing what humanity is capable of achieving. JWST's recent discovery is just the beginning of a new era in space exploration. Its success paves the way for future missions that will further our quest to understand the universe. Upcoming telescopes, both in space and on the ground, will build on JWST's findings, investigating the cosmos with even greater precision. These missions will explore everything from the nature of dark energy to the potential habitability of exoplanets, pushing the boundaries of our knowledge. As technology advances, we can expect to uncover more about the universe's mysteries, continuing the legacy of discovery that JWST has reignited. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.